Thank you to join this session. In a previous session, we had started to discuss about another type of the gas power cycle. All of this chapter actually is about the gas powered cycle, which the main characteristics or the common characteristic for different type of cycles. In this chapter is working fluid. In this type of the cycle is a gas. Generally, based on the air standard assumption, the working fluid in the cycles which we have in this chapter is air actually. In the previous session, I introduced you two different types of the gas powered cycles, which those two cycles were for the reciprocating engines or internal combustion engine. The first one was for the spark ignition engine or Otto cycle, and the second one was for the diesel cycle, which we discussed yesterday actually about this cycle. We have seen the differences between this cycle, the diesel cycle and Otto cycle. We have discussed about the processes which we have in the diesel cycle, and also you know about these processes in Carnot cycle. I've introduced you PV and TS diagram of this cycle actually. Now in this session, we are going to go see also three more different type of the gas power cycles. The first two cycles, which today I will introduce you, are just some extra knowledge which I am going to share with you. Not that much actually important compared to the rest of the chapter, but I think it is useful for you to know also about this type of the cycles. So briefly, actually, I'm going to introduce these two cycles, the Stirling and Ericsson cycle. These two actually, Stirling and Ericsson cycle, are two two type of the gas power cycle which are not that much common compared to the Otto and diesel cycle, and also the other gas power cycle which I will introduce you, the Brayton cycle. These two cycles, Stirling and Ericsson cycle, or they are not that much new type of the cycles, but they just have been recently popular for the scientists or for industry because of some interesting characteristics which these cycles have. So first of all, let's see what I mean from the Stirling cycle, or we can say a Stirling engine. We can have a Stirling engine. Now let's see what is a Stirling engine. Then I will talk about the cycle which we have for this engine actually. Let's see a short video actually to see how is the Stirling engine. Then I will introduce more. I will talk more about the cycle which we have for the Stirling engine actually. So first, let's see a short video about it. You can see a Stirling engine actually here. The Stirling engine is very useful type of the engine, to convert heat to power. You can see this engine in. Let me also close the here for myself. Then for this type of the engine actually, if we have a temperature source for that, for example here, we will fill this cup for boiling water. Then we just put the the engine, actually here is the piston of the engine, and here is the wheel or flywheel actually. In this type of the engine, usually we have two different piston in a piston cylinder arrangement. Here you can see the main piston actually, and here is the cylinder. Here is the a small piston, or we can call that the piston number one. And here is the cylinder. Inside the cylinder, we can have another piston. To run this engine, actually, we need to have a heat source and also actually a cooler or a cooler surface. So here we have a cooler temperature or low temperature. At the bottom, we have high temperature. We also have this piston, which we can call that piston number two. Shaft is attached to that, and you can see the gap between the piston and cylinder. So air can go from one side of this piston to the other side, but we have a small gap, actually not a big gap here. So here we have a high temperature. Here we have a low temperature surface actually. Once you can see here this displacer, or we can call that, moves due to the motion of the air. The air here, about that. When air temperature of the air change, its density also is changed, then it change the direction, the its place actually. So it will go from bottom of this piston to top of this piston. And the movement of this piston, as you can see also, let me just go back a little. Here, this piston, this placer, placer, or the piston number two actually is attached to this flywheel and actually a shaft, I can say, and also the other piston. Movement of these two, both of them, is transferred to this flywheel actually. You can see how it moves. The movement of one of these pistons will cause the rotation of the flywheel, and the movement the other one also will cause a halfway of rotation of this flywheel. You can see how these two works. Flywheel momentum also, as a, do you remember I told you about the regenerator? I haven't yet told you about the regenerator, but here we call this flywheel actually as a regenerator. I don't know if you have about the characteristic of a flywheel or not. Flywheel is a mechanical device, like you can see here. It is a wheel. If you have already seen the engine also, you may know about the flywheel. It is a component of the engine, a big, sometimes, usually it is a big wheel actually. If you notice, once you rotate something, when it is attached to a shaft, it will, even when you release the that wheel, it will continue its rotation. What is the reason? The inertia is the reason for the rotation of the wheel, even after you remove the rotational force actually. So here also, the rotational force which come from displacer and piston will transfer to this flywheel, and this flywheel will absorb that, then release it. This is the process which happen in the displacer actually, in the flywheel. This type of engine, you can see here, we just run the flywheel because it needs initial energy to run. Then you can see this will continue to work. I will talk more about actually the cycle and what happened exactly inside this, but this is an real Stirling engine you can see here. We can also change, the surface, the hot surface and cold surface. Here, when we put this Stirling engine on the top of a piece of ice, you can see the cold surface will be the bottom surface, and hot surface actually, or the surface with higher temperature, is the top surface. So you can see here Again, this will work. We just need to have that temperature difference between two different surface of the piston cylinder in the Stirling engine to run this engine. The interesting thing about this type of engine, if you notice here, in contrast with what we had for the internal combustion engine, here the heat source, here again we need to have a temperature difference. So it can be a heat source or it can be a heat sink actually. In this case, heat source is the environment because the temperature of the environment which is on this surface is higher than temperature of the ice which is in contact with the bottom surface. So to run this Stirling engine, we need to that temperature difference. And this temperature difference, as I said, in contrast with the internal combustion engine, is an external heat source actually. So this type of the engine are, they can use the renewable type of the energy. For example, instead of this, this is a cup full of hot water. So if we can provide hot water, or even if we can provide a surface with high temperature, for example, if we use the solar radiation, the sun radiation to warm up something, that can be a heat source. Because of this advantage of the Stirling engine, nowadays scientists have changed toward to use this type of engine, especially for the uh, uh, utilization of the renewable energy. They are quiet engines because not that much moving component, and also we have especially for the displacer because it is the most biggest part of this engine which is in motion. We don't have any friction between that and the wall of the cylinder actually. So because of that, this type of engine nowadays became a popular type of the engine, but still compared to the internal combustion engine, not that much you know uh, common type of the engine actually. So let's see how is the cycle which we have for this type of the engine. And beside what I told you about its structure and so on, how this type of the engine can be useful and what is the main advantage actually of this type of the engine. It goes back actually to the what I told you at the beginning of the this chapter. I told you always we are going to increase the thermal efficiency of the gas power cycles. We are interested to have a cycle with maximum possible thermal efficiency. And if you remember, I told you that we just can get the maximum possible efficiency for a power cycle or gas power cycle when it is Carnot cycle actually, or it is similar to Carnot cycle. And the characteristic of the Carnot cycle is all of the processes in this cycle, in Carnot cycle, are reversible. And also we have two isentropic processes and two isothermal processes. This is TS diagram for Carnot cycle. You can see here we have two isothermal processes and two isentropic processes. Constant volume and here the constant temperature actually. So let's compare the cycle which you already have seen their characteristic. The TS diagram for Otto cycle and diesel cycle. If you notice about Otto cycle, I told you that thermal efficiency of this cycle is about 30, less than 30% actually. For diesel cycle, the maximum actually uh, thermal efficiency which we could up to now get from this type of the cycle is less than 50%. So what is the reason? But for the Carnot cycle, these can be higher actually. Why? The reason is here. You can see in the TS diagram for these two types of the cycle. For Otto cycle, if you notice here, we have these two isentropic processes, but the processes which we have from state 2 to state 3 and from state 4 to state 1, instead of a constant volume heat addition, and instead of actually the isothermal heat addition and isothermal heat rejection processes are constant volume heat addition and constant volume heat rejection. Here we have constant temperature actually. So here during this process, temperature of the working fluid or temperature of the system change, and we have a temperature difference here. Here, for example, is T3. Here temperature is to T2. So during this process, we have a delta T actually. Same for the diesel cycle. If you notice here, if we want to have that maximum thermal efficiency, we need to have this isothermal process. But here you can see instead of this isothermal process, we have a constant pressure process. You know, this one is same. The process from a state 4 to a state 1 is same in the diesel and Otto cycle are similar. So this is also, you can see we have a temperature difference during this process. It is a constant volume process. And also for this one, for the process in the state 2 to state 3, which is the constant pressure heat addition process, we have that delta. And if you remember from thermodynamics, one of the reasons for the irreversibility, or one type of the irreversibility actually, is the heat loss due to this temperature difference. So the problem with these two cycles, which cause the efficiency of these two cycles be lower than the maximum efficiency, which is the efficiency of the Carnot cycle, is these processes. They are not isothermal processes actually. So actually, can we have isothermal processes here instead of this constant volume process? Can we change the Otto cycle? It means, can we change the spark ignition engine? How about here? Can we change this process for diesel engine? Actually, we always will have this problem. In other words, without this constant volume process, without this constant pressure process, these cycles will not work actually. So we always will have this irreversibility and these problems. So the efficiency of these two type of the cycles or engines actually will be always lower than the maximum possible efficiency which we can get from a cycle or from an engine which works between two maximum and minimum temperature. And also please notice here also we have the maximum and minimum temperature, but the problem is the this process. So it is also mentioned here, heat addition and heat rejection occur during isothermal condition for Carnot cycle, but for the diesel and Otto cycle, it is not occur during a isothermal condition. So we have irreversibility in the cycle. Because of that, efficiency of Otto and diesel cycle is less than Carnot cycle. Now to have another cycle with better efficiency, these two cycles, Stirling and Ericsson cycle, are introduced. The characteristics of the main important characteristic of these two type of the cycle is they have isothermal heat addition and heat rejection process. So they are engine type or cycle type more similar to the Carnot cycle. How is this processes? You can see here, this is TS diagram for the Carnot cycle, TS. and PV diagram here for the Carnot cycle. The TS and PV diagram for the Ericsson for the Stirling and for the Ericsson cycle also is shown here. But before I explain about these cycles, I need to introduce you the regenerator. A regenerator is a device that borrows energy from the working fluid during one part of the cycle and pays it back without interest during another process. Here you can see a schematic of a regenerator. A regenerator can be something like this wheel, which I show you in, if you remember, like that flywheel actually. Energy is given, it is just a schematic. Energy is given to this wheel actually during this process. Imagine, this is our working fluid. Imagine this is four different processes in this, or a cycle actually. This is whole cycle. No, this is whole cycle. This is four different state, for example. This is just a schematic, not actually real cycle. So you can see during this process, this energy is shown. It is shown as a, for example, a ball is given to the regenerator. Then it will rotate, and also working fluid will go to the other state, and finally to this process. During this process from state one to state two, this energy is given to the regenerator. And during this process from state 3 to state 4, this energy is given back to the working fluid. You can see the direction of the energy actually. We call this regeneration. And how it is useful actually, you know that if we have working fluid in this process, and to motion of the working fluid actually in the engine, and if you remember these four different processes, we don't have power in all of these four different processes. For example, if you assume this is a cycle, only in this process from state 1 to state 3 to state 2, we have power, energy to into the system. In this process from state 2 to state 3, we don't have any power input to the cycle. So the power will reduce. How about here? And to complete a cycle, we need to go to initial state in the cycle actually to have a cycle. Then this energy, if it is given to the regenerator and it is received here, it means this much of energy can be saved actually during this regeneration process. Here is just the basic concept of regenerator, and you need to know this definition as well. Later also we will discuss more about the regeneration, and you will see some real example of this regenerator in the Brayton cycle. Now let me just finish our discussion about the Stirling and Ericsson cycle. These two types of the cycle. This is, as I said, just extra information. You need to more learn about the regenerator. What is regenerator? Let's go back to our cycles. Here is Carnot cycle. You know it's TS and PV diagram. Here is Stirling cycle. You can see here in a Stirling cycle, we have that isothermal processes. This is isothermal process for the Otto cycle, isothermal process from state 1 to state 2, or isothermal heat addition process, and here isothermal heat rejection process in the Stirling cycle. How about the other two processes? The other two processes, instead of isentropic processes, are constant volume processes. If you compare this process, this TS diagram for a Stirling cycle and Carnot cycle and Otto cycle, you can see in the Otto and diesel cycle we had isentropic processes. Now those isentropic processes are substituted by in the Stirling cycle by constant volume process, in the Ericsson cycle by constant pressure processes. And heat addition and heat rejection processes in these two cycles are occurred in isothermal manner actually, as you can see here. It means, you can see also from the, the diagram which is shown here, the graph is more similar to the graph which we have for the Carnot cycle. And actually, how it is possible to have this type of the cycle? It is possible due to this regeneration. This regeneration helps to keep or to save a fraction or a part of the Q in, which is to the system, and prevent to release to the surrounding. So first, just keep in mind this this diagram for this two type of the cycle. In a Stirling cycle, we have two isothermal processes, heat addition, heat rejection, and two constant volume processes. In Ericsson cycle, we have two isothermal processes, heat addition, heat rejection, and two constant pressure processes. This is the processes which we have in the Stirling and Carnot cycle. But how this cycle actually works, how these two type of the cycle works in real world actually. For the Stirling cycle, you have already seen the Stirling engine. This type of the cycle is in the Stirling engine. We have two different pistons and a cylinder and a regenerator. What is this regenerator here? Here the regenerator is porous material actually. Here we have a gas. This gas actually can travel, can go through this porous substance. Initially, we have a piston cylinder arrangement like this. If we write the name for them, piston 1, piston 2, and here the gas temperature is TH, and here we have that regenerator. When we give Q into the this piston cylinder device or our system here, actually, temperature in a isothermal process manner, actually, the gas inside this will expand, and it will push the piston number 1 toward the left. You can see here, this number 2, no motion, and the regenerator actually does not move at all because it is just a porous substance inside the cylinder. Then once it reached its final position, the maximum possible expansion of the cylinder or the system actually, then if we force the piston, this piston number 1, all of the gas which we have here will transfer through this porous substance or porous material or the regenerator. The gas will go through this regenerator and will go to the right side of the regenerator, and it will cause the movement of piston number 2. And during this, this transfer of the gas through the regenerator, that if we have this thing in real world, some of the temperature or thermal energy, actually, I can say, will transfer from the gas to the substance. So temperature of the gas will drop to TL, which is the minimum temperature, the lower temperature of the gas, and a part of the thermal energy or Q is given to the regenerator. So during this shifting, actually, we have a Q to the regenerator. Then if we again reject the heats, from this, our working fluid, from our system to the surrounding, Q out, this will, and also we have we force the piston number 2 toward the left side, the gas again, will compress, and this Q will actually reject to the surrounding. To go back from a state 4 to complete the cycle actually to a state 1, we need to push this piston number 2 until it reaches the regenerator, and whole gas here actually will again transfer through this regenerator. How about its temperature? This compression actually is isothermal heat rejection process. How about, this gas which we have here? The gas again will travel through the regenerator and until it, goes back to its initial state. During this transfer of the gas through this porous substance, the Q which is given to the porous substance will give back to the working fluid, and temperature of the gas finally here will be TH. So, when we have Q out here, and we have a compression here, temperature remain constant, TL. But when it's traveled through this when it transfers through this substance, its temperature will increase again. Why? Because we have a hot regenerator or substance here. By this cycle will continue, and we can have a Stirling cycle actually, or a cycle by using this regenerator. Without this regenerator, it doesn't work. And you need to also notice that this process from state 2 to state 3 is a constant volume process. Why? Because as much as the volume here is decreasing, the volume at the right side of the regenerator is increasing. So here we have a constant volume process. This is for Stirling cycle. How about the Ericsson engine actually? You can see here a steady flow Ericsson engine. In Ericsson engine, we have a compressor turbine arrangement. You can see here we have a compressor. Its temperature is TL, or lower temperature. It is constant during this heat rejection process. And we have a turbine, which is temperature. The working fluid temperature in the turbine is TH, the maximum temperature. And we have heat addition for the turbine. With this arrangement, actually, here we have a gas. The gas after compressor will go to a heat exchanger here. Generally, it's later I will talk about this regenerator. The working fluid will compress and will go to the turbine. In turbine, we give the Q in actually to the working fluid. Its pressure will increase, and it will cause the rotation of the turbine, and the work is produced. And it needs to go back to the compressor. Then we have heat rejection here, and this cycle will continue. But in real world, we cannot have this arrangement actually. We can have, but its efficiency will be very low. How we can increase the efficiency in this cycle? If we use this heat regenerator, after this turbine, Q is only given to the working fluid here in the turbine. After turbine, this Q actually will go to the compressor, and all of that will reject to the surrounding. So we have a useless process actually here if we do not use a portion of the thermal energy of the working fluid here. Regenerator here actually is a heat exchanger. We can use the, after turbine, still the gas which we have here has energy. Q in will come to here, do work, produce work. Then here we still have working fluid with high temperature. Then if we use this high temperature here in a heat exchanger before it goes to the compressor, to increase temperature of the working fluid after compressor. Here is very interesting. Generally, for the compressor, as much as the temperature of the gas is lower, it will increase the efficiency. Later, we will discuss more about that. However, based on the thermal efficiency of the Carnot cycle, which I will tell you that the thermal efficiency of Stirling engine and thermal efficiency of the Ericsson cycle is equal to the thermal efficiency of the Carnot cycle. And you know that how we can calculate that? 1 minus TL divided by TH, which TL is the minimum temperature of the gas in the cycle. TH is the maximum temperature of the gas in the cycle. So our purpose here is to increase uh, TH or to reduce TL. If each one of them actually will increase the thermal efficiency of this cycle. So in the Ericsson cycle, here we can increase actually this TH. How? Because here we, in the compressor, we need to have a gas with lower temperature. How we can do that actually? If we absorb a Q portion of the Q here before compressor. And how about the turbine? We are interested to increase TH. How we can do that? We can use this Q before turbine. So we have a Q here. The Q is given to the regenerator here, and it is received again here in the between the compressor and turbine. So this is regenerator actually. Later we will see this regenerator in very useful equipment. Here for the Ericsson and Stirling cycle, what is important is this: the efficiency of these two cycles is identical to the efficiency of the Carnot cycle. And very important conclusion of these two types of cycles. The Stirling and Ericsson cycle give a message. Regeneration can increase the efficiency. So this is all you need to know about the Stirling and Ericsson cycle. Now we just will use this part actually in our next cycle. Here in this video, you will see a typical actually or the actual gas turbine engine which we have in power plants. The gas turbine engine which is discussed here in this video is a General Electric actually turbine engine, gas turbine engine, and it shows what is in a gas turbine engine generally. We have air and the natural gas liquid fuel. So here, similar to what we had for the internal combustion engine, and always like other type of these power cycles which we are discussing about them, we need to have a heat source. So heat source here again, it comes from the combustion of combustion reaction between a type of the fuel, which can be natural gas, can be liquid fuel, and air. But in the internal combustion engine, if you remember, we had that piston cylinder arrangement. What we have here in a gas turbine engine actually. In a gas turbine engine, here is just explanation about about this type of engine, which are mainly being used to produce electricity. How this electricity is produced is in this engine actually. This is a gas turbine engine. Actually this is an actual a real gas turbine engine. Its specific name also is mentioned here. The structure is like this. Here again, this is air come to this is a cylinder. This is a cylinder which we have. The air come to the cylinder. It is compressed. We have a compressor section here. Air is compressed here. Then its temperature will increase. You can see here, here low pressure, low temperature, high pressure, high temperature. Then here we have a fuel injection to this flow of hot air actually. So here is hot air, here is the fuel injection to this high temperature air. So you can see the similarity. Also for the internal combustion engine, if you remember, we had this air fuel reaction inside the chamber, but there we had a piston cylinder device. In other words, up to here especially, it is same. We have a combustion reaction, but in the piston cylinder type engine or the reciprocating engines, we had the piston to convert the thermal energy or the energy which comes from the fuel burning inside the cylinder to power, to work, or mechanical power actually. Here we have a turbine. However, you can see the similarity as well. And the main difference actually is the power output, which we can get from these two different devices. For the engine, maximum we can get 143. Higher, even higher we can get actually. But the thing is, for a gas turbine engine, the power which we can get is much higher. You can see here, if we compare 220 horsepower compared to 644,000 horsepower for this gas turbine engine. So we can get much higher power from the gas turbine engine. And this type of engine is not only being used for the uh, electricity generation. They are also being used in the airplane. The engine which we have for some of the airplane is this gas turbine engine actually. And let's see the other component which we have actually. And simply here we have a turbine actually. Here after the compressor will compress the air, its pressure will increase. The high temperature of this gas after compressor will provide the condition for the combustion. When we inject the fuel to this flow of hot air, actually, it will burn and it will cause increase in the pressure even much higher. And this high pressure working fluid or the air, we can say, will cause rotation of this turbine. Rotation of this turbine will transfer to a shaft, and that shaft can be used for different purposes. One purpose is we can connect this shaft to a generator to electricity production. And the revolution, the per minute for the turbine actually here is very high. You can see here 3000 RPM it can be. And during this process, chemical energy is converted to the mechanical energy actually. And you can see the other component, the drive shaft, which we can, in this engine, it is a little complicated. However, it is, simple. You can see here we have turbine here, but the generator is here. Simply, we have a configuration to transfer, this shaft, the rotation of this shaft to a shaft again in the entrance of this gas turbine engine, which is out of the scope for this session. Discuss about that. And simply that rotation will transfer to a generator. In the generator, electricity generator, actually, we have something simple like this. We have magnets, we have coil, we have this rotation of this shaft actually will cause movement of the electrons in the magnet, and the movement of the electron means electricity current actually. So by this electricity current or electricity energy actually is produced, and it is the electricity which comes to our house. So that is actually gas turbine engine. In next chapter, I will introduce you the vapor power cycle. We again will come back to this cycle to see how we can have a combined cycle power plant, which is topic for the next chapter when I introduce you the vapor power cycle. So the gas turbine engine has this component, a compressor, and a turbine, and also we can say a combustion chamber actually. Here also you can see the main component of this type of the engine. We have compressor, we have turbine, and that combustion chamber. This is open cycle gas turbine engine, like what you have seen. But we can assume, based, if you remember a standard assumption, we can substitute this combustion chamber by a heat exchanger, which and heat generation in this combustion chamber actually can be replaced by a heat addition process or a heat exchanger. And heat rejection process, how here similar to what we had for the internal combustion engine, the exhaust gases will go out from the turbine, but we can assume that it will we have a cycle and working fluid is keeps in the keeping the moving inside the cycle, and only the thermal energy of the working fluid is rejected to the surrounding from a heat exchanger, and we call this a closed cycle gas turbine engine, which is a useful, idealized actually cycle for to evaluate the cycle in the gas turbine engine. But how we can find a cycle, how we find those processes, and how we can define a cycle for the combustion which we have in a gas turbine engine. The cycle which we have for this type of engine is Brayton cycle, which is an ideal cycle for this gas turbine engine actually. This cycle includes four processes. We have two isentropic processes. We have isentropy from state 1 to state 2. We have a process in the compressor. And if you remember from thermodynamics, in the compressor, we have a isentropic compression process actually. So from state 1 to state 2, which is in the compressor, we have isentropic compression process in the compressor. From state 2 to state 3, we have a constant pressure heat addition process. Q into the system to the cycle is in this process. So from state 2 to state 3 in this heat exchanger, or even now in the combustion chamber, we have a constant pressure heat addition. From state 3 to state 4, between heat exchanger or between combustion chamber and the turbine, or after turbine, or the process which we have in the turbine, we have again an isentropic process, but this time the isentropic process is expansion process. So we have two isentropic processes in compressor and turbine. And also from state 4 to state 1, the process which we have in the heat exchanger or for the heat rejection actually is a constant pressure heat rejection process. So we have two constant pressure and two isentropic processes. Constant pressure processes in the heat exchanger and isentropic processes in compressor and turbine. And during this cycle, the work is produced by turbine. So the work which we can get is between state 3 and state 4. Between 2 and 3 Q in, between 4 and 1, we have this Q out from the system. Now, let's see how we can draw the TS and PV diagram for Brayton cycle. As I told you from state 1, this is TS diagram. We are going to draw the TS diagram for the Brayton cycle. From state 1 to state 2, we have isentropic cycle. For isentropic cycle, you know that we have a vertical line actually. So from state 1 to state 2 like this, and temperature in the compressor is increased actually. And from state 2 to state 3, we have a constant pressure process. It will be like this. and it is actually heat addition process. And from state 3 to state 4, or in the turbine, we have again an isentropic process, but this time it is expansion. So its temperature also will drop. From state 4 to state 1, we have a constant pressure heat rejection process. Similar to the Carnot, Otto, and diesel and dual cycle, actually, you need to know also this cycle, how it is in TS diagram. So simply, the TS diagram is like this. And how about PV diagram? PV diagram of this cycle is like this. From state 1 to state 2, we have a isentropic process. You know, from thermodynamics, the isentropic process in PV diagram is like this. And from state 2 to state 3, we have a constant pressure heat addition process. And from state 3 to state 4, again, the isentropic or constant entropy process. And from state 4 to state 1, constant pressure heat rejection process. And you can see here, just let me tell you something here, that if you notice here, we have constant pressure processes here. And it is a useful thing to have higher thermal efficiency. Now let's see how we can calculate thermal efficiency for this cycle. Similar to what we had done for the Otto and diesel cycle, we will use energy balance equation. Q plus W equal to delta E. But here, again, you know that delta E is equal to delta K plus delta P plus delta U. And here we ignore change in the kinetic and potential energy, and we use that air standard assumptions. If you remember, the working fluid is air, so we have air standard assumption. Assumptions in our calculation actually. Then by these assumptions and by this as well, we can write energy balance equation for the cycle and also the processes which we have here. For the whole cycle, we can write this equation: Q in minus Q out plus W in minus W out equal to H exit minus H inlet. This is the general equation for whole cycle. But now let's see how we can find thermal efficiency. If you remember from previous session as well, the thermal efficiency of any heat engine, this engine which we have here also is a heat engine, can be calculated by this equation: W net divided by Q in, or the total work which is output of the engine divided by the what is given to the engine, which is Q in. So this is general equation. And as I told you, you know that W net is equal to Q in minus Q out. So if we substitute here, this equation will change to this 1 minus Q out divided by Q in. Now, if we have Q out and Q in, we can calculate thermal efficiency. But generally and usually Q out and Q in cannot be measured actually, and it is not easy to measure this heat, which is the thermal energy or energy which is transferred to the cycle. So it is better to work with temperatures, because temperature can be easily measured by a thermometer. You can measure, and it is properties which is under your control and easy to measure. So how we can have equation to calculate thermal efficiency of Brayton cycle based on the temperatures in the different states. Again, we can write energy balance for each process. Q in is in this process from state 2 to state 3, which is a constant pressure process. So we can write Q in equal to H3, the enthalpy at this state, and here enthalpy at this state. you know why we use enthalpy here. Sometimes we use enthalpy, sometimes we use, you know, the internal energy. Actually, enthalpy is equal to PV plus U. So here the process which we have here, actually our P is constant, but volume is changed. So we need to have both of these uh, two type of the energy. So here we need to use H3 for a constant pressure. We use constant pressure process. We use enthalpy. So Q in come to the system is equal to the, you know, this is the reason why the energy changed during this process, due to Q in. So we have only Q into the system. How much energy is changed during this process due to this heat addition is equal to the energy which we have here minus energy which we have here. Energy here, you know, it is enthalpy because we ignore the P and K, or potential and kinetic energy. So we have only enthalpy, H3 minus H2. And from thermodynamics, you know, for ideal gas, we can write this equation in a process from for in a process which is from one state to the other state. So H3 minus H2 is equal to Cp T3 minus T2. Cp, why Cp or constant pressure specific heat? Because here we have a constant pressure process. So we have this equation from thermodynamics. Similarly, for Q out, we have another constant pressure process. We can write similar equation, but this time we have Q out H4 minus H1 actually. And you know why it is changed actually, because Q out here is negative. So you know, instead of H1 minus H4, it is H4 minus H1. However, it is you know, the amount, the value is same if you write H1 minus H4, but the sign will be negative. So the right form of the equation is like this: Q out equal to H4 minus H1, because here the energy is going out from the cycle. Now we have an equation for Q in and Q out based on the temperatures in those four different states, and also specific heat out working fluid, which is air actually here based our assumption, air standard assumption. Now let's just put the Q in and Q out in the equation. 1 minus this Q out and Q in, cross out this, and this is the equation actually. Simply, if we have T4, T1, T3, and T2, we can use this equation to calculate thermal efficiency of Brayton cycle. So this is the initial equation actually to calculate the thermal efficiency of Brayton cycle based on the temperature. Now let's continue and find out how we can make this equation easier to understand and to evaluate actually. If we bring out T1 from this term and T2 from this term, we will have this equation. And you know, from thermodynamics, for an isentropic process, we have this equation or relation between temperatures and pressures in that specific process. Here, for this process from state 1 to state 2, from state 3 to state 4, we have two isentropic processes. Then we can write T2 divided by T1 is equal to P2 divided by P1 power K minus 1 divided by K. Here, K is the specific heat ratio, which for the air, K is equal to 1.4. So we have this equation from thermodynamics for isentropic process. Similarly, we can write this equation for this isentropic process from state 3 to state 4. And if you notice here, because here pressure at state 2 is equal to the pressure at state 3, because we have a constant pressure process. And similarly for state 4 and 1, the pressures are equal, P4 is equal to P1. Then we can say, finally, we can say that T2 divided by T1 is actually equal to T3 divided by T4. Then if we substitute the information which we have here in this equation, we will reach another equation based on the pressures actually. I'm not going to go through that, but if you just substitute instead of T2 divided by T1 this equation, and instead of T3 and T4 this equation based on pressures, then if you define this parameter as well, P2 divided by P, or pressure after compressor, the pressure ratio. P2, is pressure after compressor. P1 is the pressure before compressor. It shows how much the air is pressured in the compressor actually. If we define pressure ratio like this, RP equal to P2 divided by P1, then the equation to calculate thermal efficiency of the Brayton cycle based on the air standard assumption is this 1 minus 1 divided by RP power K minus 1 divided by K. So if we have RP, or pressure before and after compressor, or if we have pressure ratio actually, then we can calculate if we know what is the working fluid, here usually the working fluid is air, so we know the K usually is 1.4. So only RP is required in this equation to calculate thermal efficiency of a Brayton cycle. Based on this equation, we can draw this graph. And also, if you notice here, as much as pressure ratio increase, it means this increase, then total term here will reduce. And finally, Brayton's thermal efficiency of Brayton cycle, this is 1 minus something. If this A, for example, is reduced, thermal efficiency will be higher. 1 minus lower A, bigger thermal efficiency. So by increasing the pressure ratio, thermal efficiency of Brayton cycle is increased generally. This is what you need to know about the Brayton cycle relation with the pressure ratio. So you can see also the typical pressure ratio for gas turbine engine. You can see it is between 5 to 20. The typical pressure ratio for the Brayton cycle. And as I told you, for air propulsion and also for electric power generation, this cycle is being used. The other important thing about this Brayton cycle is the highest temperature in the cycle is limited by the temperature that turbine blade actually can withstand. So here, in the cycle which we have as well, later you will see also more about that. The higher temperature, the higher maximum temperature in the cycle will give us the higher thermal efficiency. But we have a limit. That limit is the maximum temperature that the turbine blade can. This is the limit for the increase in the temperature, maximum temperature in this cycle. And also here, because we are going to have higher efficiency actually in the cycle, and the size of the engine actually is not comparable to the internal combustion engine, then air-fuel ratio actually is too much high compared to the internal combustion engine. And air-fuel ratio for this type of the engine, air-fuel ratio means how much air is going to react with the fuel, the combustion reaction between air and fuel. So 50 units of the air is reacted with the 1 unit of the fuel. So air-fuel ratio in this type of engine is also very high, and it is useful to cool down the component of the turbine and engine actually for this reason, to reduce to provide the cooler temperature actually in some part of the cycle. In the turbine, we need to have maximum temperature, but after turbine, it is better to have lower temperature. So air-fuel ratio is high in this type of the cycle to cool down after turbine usually actually. And also you need to know about back work. If you notice, we have work output from this engine from turbine, W turbine. But all of these work which we come from turbine is going to be used for example, electricity generation. No, a portion or a fraction of that need go back to the compressor. If you see the arrangement here, you know the compressor is attached to the turbine by a shaft. So, and you know that the compressor needs a power input. Compressor use power to compress the a kind of fluid, which is air, for example, here. But turbine receive the fluid flow and produce the power. So here, power is produced by turbine. A fraction of that will be used to electricity generation and so on. And a portion or a fraction of that will go back to the compressor to run the compressor. We call this back work. And the fraction of the turbine work which is used to drive the compressor is called back work ratio, or simply W compressor divided by W turbine will give us the back work ratio, which later I will discuss about that as well in the example. But here, one question may come to your mind about the relationship between the correlation between the thermal efficiency of Brayton cycle and pressure ratio. So why we do not increase this pressure ratio? First of all, you can see here, if we increase the pressure ratio, the thermal efficiency of Brayton cycle increase. Why we have this limit, for example, 20? Because we have some limitation. First of all, the compressor needs to be, the efficiency of the compressor needs to be high. Later I will discuss about that. Moreover, here, if you notice the thermal efficiency of the Brayton cycle with the increase in the RP, initially it increased, but you can see here, it is a start to even to reduce. We can show that on this graph, in TS diagram. When RP change, when RP, for example, is equal to 2, the cycle will be this one. You can see here. How we can calculate the W net for this cycle? This is Brayton cycle when RP is equal to 2. The Brayton cycle work output, to calculate the work output for a cycle in TS diagram, simply we can, find the area inside that cycle. So when RP is equal to 1, the cycle is this one. So the work output is this area. When RP is equal to 2, RP means pressure after and before compressor, the ratio of that actually. When RP, RP is 2 here, when we increase RP, initially actually that the efficiency of the cycle or the work output of the cycle increases, then it reduces. Based on this equation, actually, we can include that. So initially RP increase until it's reached, initially by increasing the RP, W net also is increased until it reaches a maximum, then it will start to reduce again. You can see here RP is equal to 2 here. You can see the work output is this area. When RP is equal to this 8.2, the work which we can get this area bigger than this one, and by increase more by more increase in the RP, for example, RP equal to 15, then this W net max actually will reduce to this area. You see the cycle, the Brayton cycle, when we have RP equal to 50. How we can find this RP, which give us the maximum W net max? W net max is can be the output of the Brayton cycle when RP is equal to this equation. T max divided by T mean power K divided by 2K minus 1. In other words, we have an optimum RP, which in that RP we have maximum possible work output of the cycle, which you can see it depends on the Tmax and Tmin. If you have Tmax, if you have Tmin, you can, and you know what is the working fluid. If working fluid is, for example, air, K is 1.4. Then simply you can calculate RP for that cycle, which gives you the maximum possible W net. So you can see here how we can calculate the thermal efficiency for Brayton cycle and how it changed with the pressure ratio and what are the effective parameters for the efficiency of the Brayton cycle. We always, as I told you before, we always are interested to improve the efficiency of different cycles. Now here, how we can increase or improve the efficiency of Brayton cycle. What we can do are three different methods. We can increase the turbine inlet or firing temperature, or Tmax actually, or we can increase the efficiencies of turbo machining. So now we are interested to improve the efficiency. How we can improve it? First of all, in actual cycle, the Brayton cycle, what I told you here up now is about ideal Brayton cycle. And we say that in ideal Brayton cycle, we have isentropic processes in the compressor and in the turbine. And also we have constant pressure in the heat exchanger, or actually in the combustion chamber. But in real world, we don't have something like that. We have deviation from the isentropic process. Why? Because we have some irreversibilities in the turbine, compressors, and so on, like pressure drop, which we have in the turbine and compressor. We assume we have isentropic process. But due to the heat loss, actually, and also due to the pressure drop, the process which we have in the turbine and compressors are not isentropic. The isentropic process means from state 1 to state 2S, a vertical line on TS diagram for the compressor. For the pump, also a vertical line, state 3 to state 4S. This is for ideal one, but for the actual Brayton cycle, it is like this. It is not an isentropic process. We have some irreversibility. The entropy will increase in the compressor and also in the turbine. So the turbine and compressor are not isentropic devices actually. Then we need to, then how we are going to calculate the efficiency of the cycle? We use idealization to find this equation. So here we understand that the actual cycle is not include isentropic processes. How we can calculate the thermal efficiency now? We can use some equation which you have already also seen in thermodynamics. We need to use isentropic efficiencies of the compressor and turbine. What is isentropic efficiency? You know, when a compressor and a turbine is ideal, or actually there isn't any irreversibility for the compression or expansion process, we say that it is isentropic process. But when we have that irreversibility, when we have a pressure drop, when we have a heat loss in those equipment or devices, we have an actual process. So we can write this equation. For example, for the compressor, we can use this equation. The isentropic efficiency for compressor is equal to Ws divided by Wa. Ws is the work output from the for an isentropic compressor. Ws work output for isentropic compressor. Wa is the actual work from a compressor actually. Then Ws divided by Wa will give us the isentropic efficiency of a compressor. If the compressor is isentropic, actually this will be 1. As much as it is closer to the isentropic process, the process which we have in the compressor, the isentropic efficiency will be higher. Same, we can find this for the turbine, the isentropic efficiency for turbine, WA divided by WS. WS here means this. Here WS is given to the compressor, but here WA is given to the compressor. Simply we can calculate it. H2S minus H1, the change in the enthalpy. And how about this process, the actual process in the compressor? H2A minus H1. And in the same, by same procedure for turbine, H4S, H3 actually minus H4A will give us the actual work output here, the work output. We have WS for turbine, WA for turbine. So here, this is the ideal one, isentropic one. This is actual one. So the actual H3 minus H for A, the isentropic one, H3 minus H4S. Why here WA is equal divided by WS? Here WS is equal is divided by WA, because usually the required work input for the compressor is the actual one is higher than the isentropic one due to irreversibility. About the turbine, generally the actual work output which we can get from turbine is less than the isentropic work which we can get from the turbine due to the irreversibility. Now let's see what are the other, this is actually the first thing. What is the deviation of actual cycle, the actual Brayton cycle and the ideal Brayton cycle, and the reason also is mentioned here. Now the modification which I told you, we can add a regenerator to this gas turbine engine to improve its efficiency. So the thermal efficiency of the Brayton cycle increases as a result of regeneration. How? Because it will cause reduction in the fuel consumption by the cycle. As you can see here, we have a turbine, combustion chamber, we have compressor, we have combustion chamber, we have turbine, and the work output. What is added here is this regenerator, which I have already told you about that. Here, a portion of the Q is given to the regenerator. Then, during this process from state 2 to state 5, this Q is given again back to the working fluid. Then here we need less Q in for the combustion chamber actually, because some of the Q come from regenerator, which I have already discussed about that. Actually, in the cycle also you can see from state 1 to state 2 is state 3 to state 4. The cycle is this, the actual cycle, the ideal cycle Brayton actually. The regeneration role is this part. Here, this is given back to the cycle here. This amount of Q is the Q regenerated. The Q which is given back or in the cycle actually can be calculated by this equation. Q regenerator actual one is equal to H5 minus H2. Here, H5 minus H2. This is the actual regenerated Q actually, and regenerated the max. We assume that all of the energy which is given to this heat exchanger during this process is given back to the working fluid during this process from state 2 to state 5. But generally, due to the heat loss in the heat exchanger as well, we will have a actual Q regenerated and maximum Q regenerated. So the actual one is this one, H5 minus H2, and the maximum one is when it is equal here H5 prime minus H2. We assume all of the Q is given back to the system, and which is actually identical to H4. H5 prime is equal to H4, for example, minus H2. So simply by this, we can calculate another parameter, which we call that effectiveness of a regenerator. How much a regenerator is closer to its maximum capacity actually can be calculated by this equation. Epsilon is equal to Q regenerated, the actual one, divided by Q regenerated by the maximum one. H5 minus H2 divided by H4 minus H2, which are calculated here actually. And under cold air standard assumptions, you know that this is actually because these two are constant pressure, so Cp is for both of them. Not here actually. Here we have Cp times cross out this. Then effectiveness of the regenerator based on their air standard assumption can be calculated by this equation, which only needs the temperature at these 4 different states. States are shown here actually. And under cold air standard assumption, these the thermal efficiency of the Brayton cycle when we have regenerator will be like this. This is also important. Thermal efficiency of Brayton cycle with regenerator is equal to 1 minus T1 divided by T3 Rp as the pressure ratio power K minus 1 divided by K. So you can see here the thermal efficiency of the Brayton cycle with regenerator depends on the ratio of the minimum to maximum temperature and also the pressure ratio. And the regeneration is most effective at lower pressure ratio and low minimum to maximum temperature ratio. This conclusion brings out from this equation. So in this equation, if we reduce T1, which is here the minimum temperature, or increase T3, which is the maximum temperature, then we can increase the thermal efficiency of using Brayton cycle with regenerator. And you can see a difference between the Brayton cycle with and without regenerator. When we have regenerator in the cycle, the efficiency of Brayton cycle decreases with increase in the pressure ratio. You can see here, and also you can see here. If we increase Rp, all of these terms increase, and 1 minus something bigger, will give us the lower thermal efficiency for a Brayton cycle with regenerator. But when we don't have any regenerator in the cycle, this equation was like this actually, if you remember. If we increase this Rp, then efficiency increases because of this equation. So all of these graphs actually are drawn by the information which we can get from this equation. So when we have regenerator in the cycle, it is better to have lower pressure ratio, as you can see here as well. Low pressure ratio, higher thermal efficiency of the Brayton cycle. And the modification which I told you. So here I told you that if we reduce the lower temperature and increase the maximum temperature, the efficiency for a cycle with regenerator will be higher. So we use intercooler and reheater. What is intercooler? We use intercooler to reduce that minimum temperature, and we use reheater to increase that maximum temperature. For example, usually in the actual, we use a multi-stage Brayton cycle, or actually the gas turbine engine. As you can see here, for this type of the gas turbine engine, you have 2 compressors, for example, 2 turbine, and between compressor, we put the intercooler. What is the role of intercooler? it will reduce the temperature between these two compressors from state 2 to state 3. Because, you know, in the compressor, due to the compression, the temperature of the working fluid will increase. We use an intercooler again to reduce it for the second compressor. Then it will go to the regenerator. You know that we need to have a regenerator to increase the efficiency. Combustion chamber to a turbine. Again, after turbine, you know, the temperature of the gas will drop due to the irreversibility we have, and so on. Then in the reheater, again, we use a, you know, another heat exchanger or any other energy source, for example, to increase the temperature. Again, we use another turbine to use power, to produce power. So here, two turbine will produce power. And two, you know, here, because we have two compressors here, so we need, you know, the work, the power consumption should be calculated for two compressors. The power production also is in two turbine. But here, which compressor, you know, what should be characteristic of the compressor we put here? And is it important how much be the size or the properties of the compressor which we put here? We have a criteria for that. If we want to have minimum required work for the compressors, and if we want to have maximum work output from the turbine, it is better to have this equation. P2 divided by P1 be equal to P4 divided by P3. P2 divided by P1. The pressure ratio for compressor 1 be equal to pressure ratio for compressor 2. And same for the turbine. The pressure ratio for the turbine actually, or the pressure at state 6 divided by pressure after turbine number 1 be equal to the P8 divided by P9. Pressure before turbine 2 divided by pressure after turbine 2. So if we have this criteria, we can get maximum possible work output, and we need minimum power input requirement for the compressor. And TS diagram for such a cycle can be drawn like this. TS diagram, as you can see here, from state 1 to state 2, we have compressor, isentropic process. From state 2 to state 3, we have an intercooler. In other words, temperature will reduce. You have temperature will reduce, and so on. The rest of this graph also can be drawn like this. And this is also important, the regeneration part. From state 9 to state 10, here you can see from state 4 to state 5, actually, as you can see here, the Q is given back to the system, and from state 9 to state 10, this much of Q actually is saved. So this is actually more realistic type of the Brayton cycle, which we have in real world. The multi-stage, or actually here two-stage compressor, compression, and two-stage turbines in the cycle. But if we increase the number of the intercooling, reheating, and so on, it will increase the efficiency of the cycle. Why? Because if you notice here, you know, if you compare this TS diagram with the previous one, you can see it is almost similar. But here we have multi-stages. Then this process, you know, is constant pressure. And this process, also the heat addition and heat rejection process also will be closer to the a constant constant temperature process or isothermal process, and it is closer to the cycle which we have for the Carnot cycle. So, and or Ericsson cycle, which, if you remember, it is closer to the which the efficiency of the Ericsson cycle is identical to the efficiency of Carnot cycle. So in real world, we have multi-stage compression with intercooling. We have multi-stage expansion with reheating. The reason also is mentioned here to increase the power output of the turbine and to reduce the power input for the compressor. And this graph PV diagram, actually we had this graph actually in the thermodynamics as well, which is for a process from state 1, for example, to state 2. Then we have different approaches. We have isothermal approaches, which give us the maximum possible work output in this PV diagram. But generally, we have a polytropic path. If we don't use any intercooling, it will be like this. Then the required work input actually will be this much, high work input requirement, this amount. But if we use intercooling, this amount of work will be reduced because the path of this process will be like this. Then the work input, for example, imagine this is a compressor in a compressor. Pressure here P1 is increased to P2. So here is a compressor in a compression process in a compressor. Then if it is isothermal or if it is isothermal process, the required work is much. If it is not isothermal, if we don't use intercooling, the whole of this is required work input. But if we use intercooling, this amount of work can be saved actually. So simply, you can see why this intercooling is important. So by this, we reach end of today's session actually.